Assalamualaikum and good day everyone. Okay, now we're going to go to our week 11 lecture. Okay, which is about our week 11 lecture, which is about chapter 7. Okay, it's all about latches and flip-flop. Okay, chapter 7 latches and flip-flop will be extend until week 12. Okay, so today the recording is made on the 22nd of May 2021 and the timing is 1:03 AM. Okay, so this chapter is at the page of 131 of the module. Okay, so you guys can read for details. I will do some reading as well, but more to summarization. Okay, because we don't have like that time largely to cover every little words. Okay, so in the previous chapter we have studied combinational logic circuit. Okay, now we we are introduced to the terms a sequential circuit is defined output as a function both its present input and past input. So actually sequential circuit is a circuit which have the function of first present input and second past input, means it will consider past input as its function. So there will be a loop back. Okay, what does it mean by loop back? It will be some loop back, for example, from the output going back to the input. Okay, means there will be some reference of the past inputs that will be considered. Okay, this past input can be taken from your output. Okay, now to remember previous input sequential circuit depends on storage elements. Okay, storage, the fundamental storage element of sequential circuits are latches and flip-flop. So you guys must remember is that the storage element, the fundamental storage element of sequential circuit, which each is a latches and flip-flop. Okay, these building blocks are divided into three groups, which we have ungated. Okay, first we will introduce the concept of sequential circuits. Okay, sequential circuits. Then sequential circuit is have a function which consider present input and also past inputs. Okay, then in order to remember the previous inputs, okay, it must have storage element. Okay, so the fundamental of storage element is latches and also flip-flop. Okay, then these are further subdivided to ungated latches, gated latches, and also your flip-flops. Okay, so these sequential circuits, can be divided into, first is synchronous and second is asynchronous. Okay, so you guys will make a greater mind map than me. Okay, so and then synchronous is we have synchronous and asynchronous. Some sequential circuits are asynchronous, which means they are activated by any change in input value. Okay, so you can read the definition in front of the books. However, nearly all sequential circuit is synchronous. Okay, what does it mean synchronous? Is that it use clock. Okay, it use clock to trigger. Okay, it use clock. Output change only after the arrival of the clock pulse. So we have a clock pulse. So the advantage of synchronous is simplicity. So you guys can read for more detail. Now we go for the next is the clock. Okay, so what do we want to understand about the clocks? Okay, so the clocks is before we learn about the sequential circuits. Okay, we introduce the concept of clocks. Okay, in synchronous digital system, okay, all output change in synchronous. Okay, in synchronous, all output change, okay, output change simultaneously with the arrival of clock signal. Okay, now a clock is a circuit that generates series of pulse. Okay, so clock is speed is generally measured in megahertz or million of pulse per second. Okay, you guys can read here. Okay, you can pause the screen and read it. Okay, for those that didn't have the book. Okay, so it can generate measure in megahertz, in gigahertz, and so on. But the concept that I want to show is that, okay, how we identify that it's a clock or not clock signal. If we have a fixed period, I mean the fixed pattern like this, for example. Okay, so for example, for complete period is T1, correct? Am I correct? And the similar here, the complete period is T2. Okay, so we know that T1 equals to T2 and so on, right? So this is considered a clock signal. Okay, conversely, the non-clock signal having ununiform patterns for this one. You see this one? So this is a not clock signal. Okay, so I think you guys can read. Okay, and then we have a level trigger and edge trigger. This one is very straightforward. Level trigger is triggered by the level, and the edge triggered is by changing in the edge, whether it's from low to high or high to low. Okay, I think this one is quite understandable for those didn't have the module and even the Thomas and Floyd. You can see from here. Okay, now before then we go to this ungated latches. Okay, so we have, you see just now, storage element. Yeah, its fundamental is latches and flip-flop. And first is we go to the ungated latches. Okay, ungated latches is the simplest form of memory circuits that require minimum logic gates to build. As the name suggests, latches used to latch onto a logic value and retain it. So first we have for the ungated latches, we have bistable circuits. Okay, what is bistable circuits? Okay, you have this is the example, okay, of bistable circuit, which is the ungated latch. Okay, so what we can see is that is a circuit that is stable in either 1 or 0 value. Okay, 0 or 1 value. So it has memory because the value does not change unless changed by the user. Because you see, if this is 0, for example, is 0, right? Going through is 0, 1, and then 0. Okay, it's always having 0 or always having 1 unless changed by the user or part of the system. Now, this building circuit is we achieve by cascading to inverter. Okay, so this is the basic structure to what we use as the static random access memory. Okay, static random access memory. I think you guys quite familiar, right, with the term this RAM. Okay, when you buy laptops. Okay, so this is one of them. Okay, this is the complete name, which is a random access memory. Okay, so this bistable circuit is a building block of this SRAM. Okay, so if we want to set initial value to this bistable, can we do that? No. Okay, so how are we going to solve that? So we need to introduce something so that we can introduce an initial value. Okay, so what we can do is that we cascade. Okay, the loop can be broken and controlled. Okay, so this what brings to the next. Okay, to the next chapter, where is the SR latches. Okay, so go to the next one, which is the SR latches. Because this one we don't have initial value. How we're going to have initial value? So we can have of a SR latch. Okay. So SR latch is actually, you can see, okay. So let's say the circuits, okay, the SR latch. You can see this is the logic symbol. Okay. This is your inputs. Okay, which is S and R. Okay, S is actually can be meant by set and R is actually reset. Okay, and Q and Q bar having the S the output, and Q plus and plus. Plus means next output. Okay, future output, or future output and present output, or you can put this one as past output and this is present output. Whatever it is means this one is later than this one. Okay. So, you guys can read this for your convenience, okay? But I just jump to the operation, okay? Now, while both inputs are both low, the feedback maintains Q and Q bar. When S is given high pass while keeping R low, the output changes to Q1 and Q1 0. When R is given high pass while keeping S low, the output changes to Q0 and Q1. Okay, so if you want to maintain the outputs, okay, we should put, okay, S and R to be both 0. You can see, if S and R are both 0, you will always have the maintains. Okay, you will maintain the output that you have. Okay, which is either 0 or which is either 1. Okay, of course this one is just inverted. Okay, but when you start having R as 1, okay, when you set R as high and S as low, okay, here when you set R is high and S is low, the output will change to Q0 and Q bar 1. Okay, the output will change. Okay, it's just like reset. Okay, 0 to 1, and then it goes another for S01, then we reset again, so it become 1 0. Okay, then after that, when S is given high pulse while keeping R low, the output changes to Q1 and Q0. Okay, now when you have S which is high and this one is 0, okay, it will set 0, Q as 0, and this one is 1. Okay, so you guys can try this on your own. Okay, and then we see the function. Okay, we try to understand, okay, the function. Okay, this one is the SR latch characteristic table. So you have possible two combinational inputs. You can have 0 0 0 1 1 0 1 1. When it is 0 0, the future output will follow the past output, which is Q. Then when you start to have R is 1, then your Q will be reset to 0. This is what we call as reset. Okay, and then when we have 1 0 is called as set, and this one is forbidden. Why? Okay, we see what does it mean. Okay, they mentioned here. Okay, now when R and S are given high logic values simultaneously, the latches enter a restrict condition where both outputs are low. Means you will have Q and Q which is low if you have S and R both high at the same time, which is forbidden. Why? Because you cannot have Q bar and Q as similar, right? It should be contradict to one another. Okay, then so we try to understand from this table. Okay, and from this cross couple NOR gate. Okay, so we just draw SR latches. Okay, first just actually like this to draw it, and then simply taking this one here and taking this one, okay, like, okay, so you get your SRHS. So this is your R, this is your S, this is Q, and this is Q bar. Okay, imagine that for Q, okay, we take Q and we have Q plus, okay, in black color. Okay, I don't know if this obvious. Okay, it's obvious. So let's say we imagine this, the previous current output 0. Okay, of course when this is 1 means Q bar is 1, right? So I just focus on this. So let's say this one is Q0. Okay, so it will flow to here 0, and when this is Q0, so this means that this is 1, so it will follow 1 here. Okay, then what if we have SR which is both 0, okay? Oh, sorry, this one a bit error, okay, is here. I'm sorry. So it's go to here, okay? So what if your S is 0, okay? Now 0, 0 or will result in 0, but you have a inverter, so it will be 1, okay? So you can see the next, which is Q plus, is 1 for the Q bar, okay? And how about this one? 0, 1 will be 1, correct? Am I correct? 0, 1 will be 1, but because you have inverter, then it will be 0, okay? You can see when you set SR both 0, okay, just like what the book say, the feedback maintain the Q and Q bar, okay? It maintains the previous the future output will maintain the value of the previous output, okay, Q plus. You can see this is the future output, or you can say is present input, output. Then we will say as a past output. It's the same, okay, just that this Q plus is after, okay. So you can see this is for the retaining. You guys can test for the other value, okay, for the other value, and so to help your understanding, important is you do the exercise, try, okay, to do this and to try to achieve that. And then we are introduced to the timing diagram. You can see here, if you have SR is this one is 0, this is 0, means then what happened to your Q? What happened to your Q? It is for example, it will just follow from the previous is 0. Let's say if you have your S is 1 and this is 0, then you will have some set. This one will become 1, okay. Then you will try this at home, okay. And then we can see if you have SR which is both high. Where is it? Both high. Okay, if you have S and R is both high, then both of your output will be low, which is forbidden. Okay, this is forbidden because Q and Q bar should have the different value, right? If this is 0, this should be 1. So this is forbidden. So we cannot have this. Okay, this is forbidden. Okay, now the variable Q in the characteristic table represent the present state. The symbol Q plus represent the next state, or what the value will be given will be with the given inputs. So this is the timing diagram. Now we go to the next. Okay, in the improvement of this can be say improvement, okay, or maybe variation. So a variation of the SR latch can be built using NAND gate. Okay, if you see this one is SR latch using the NOR gate. Okay, this one is the SR latch is by using the NAND gate. Okay, I think this one is if I'm not mistaken is related to De Morgan's theorem. Okay, but never mind, you guys should remember that. Okay, so now what is different is that we have the same gate, the same circuitry, but the gate is changed from NOR to NAND. Okay, so by having this kind of combination, okay, the difference that you have, okay, the difference that you have for this SR is using NOR gate. Okay, then you have SR, which is using the NAND gate. Okay, you see what is the difference? Okay, so I just use Q plus. Okay, Q plus, because you can have Q plus bar is just the same, it's just you inverted it. Okay, so you have SR, SR, S and R. For the normal, okay, for the original, okay, is you just list down first the same combination. For the original, if you have Q plus and SR00, you will maintain the previous output. Okay, and if you have 0 to 1, what will you have? You will have reset to 0. Okay, then what will happen if you S1 and R0 means you set the value to 1. And what is this? For the SR latch, it is forbidden. Okay, because this at this stage, Q and Q plus, okay, both of them are 0, which is not correct because it should be contradict to one another. Now we can see the S. Now we go to the next one is SR latch with the NAND gate, S bar, L bar. When it is 0, okay, it is 0, your Q plus bar okay, contradict with this. This one is when you have both 1, it will be forbidden. But this one, if you have both 0, it is forbidden. So what happened here is that you will have 1 here, forbidden. This one is forbidden with 0 at both output. This one is forbidden at both output with value of 1. Okay, means this says is that you have Q equals to 1 and Q bar is also equals to 1, which is forbidden for the NAND gate. However, when we go to the next stage where we have S, okay, I forget to put the bar. So now 0 and 1, what happens 0 and 1? So means this is one, this is your set. Okay, you see this active, right? So what happens is that this one will be your 1. Okay, and then after that, this is what we call as set. Okay, this one is forbidden. This one is forbidden. This one is a set. Okay, this one is reset. This one is no change. Okay, so S set 0R, so this means that it will have a reset here. Okay, what reset is that we will have 0 here. Okay, then this one what happen means nothing change for this SR, S bar, R bar. So it will follow the previous output, which is no change at all. Okay, so then so you can see after that we go to the gated latches. Okay, we go to the gated latches. You can see we go from the latches, we have ungated latches, we covered that, and then we go to the next one, which is the ungated latches. Okay, ungated, we go to the next one is the gated latches. Okay, so for many applications, it is useful for the latch to enable its input only at certain time. When disabled, the output cannot change regardless of what is happening at the inputs. A latch with an able input is called a gated latch. Remember the definition, because you can get this in your quiz or in your test, in your final, whether you can able to differentiate or not, the differentiation of between this chip and this chip circuit and this circuits. Okay, so you can see here mentioned is that a latch with an able input is called a gated latch. Means that if it doesn't have enable input, it will be ungated latch. So am I correct? So you have enable here. It is difference with the ungated latch because it have enable. So called the gated latch So called because the enable signal control a gate through which the main control's input must pass through. Okay, here. Now, for the gated for the gated latch, we have two. Okay, we have two, which is the gated SR latch. Okay, we have gated SR latch, and next we have gated D latch. Okay, so you can see, right, you can create your own brainstorm or link. Okay, so it will be better. This one is for the sake of teaching. Okay, and also I cannot write very nice, otherwise it will take time. Okay, so just to see you the linkage of between them. Okay, so now gated latch, and you have under them is gated SR latch and also gated D latch. Okay, so let me go for the first type of the gated latch, which is the gated SR latch. Okay, the gated SR latch, okay, or clock latch. Okay, this one, the name is gated SR latch or clock SR latch. Okay, with two AND gate added to enable or disable. So we will use AND gate to enable or disable the S and R inputs, as you can see from here. Okay, so we have two types of gated SR latch. We have the NOR type, and we have the NAND type. Okay, you can see the difference here. Okay, if it's a NAND, you will have this kind of connection. So it is good if you can understand, but because if you try to memorize totally, it will be very exhausting. Try to memorize all of the chips. You will see, I think by now you already know that it's a lot of chips that you need to memorize. Okay, if you want to memorize, which is not easy, so it's better to understand. Okay, so but of course sometimes it requires some minimal effort of memory. Okay, because understand alone is good, but sometimes you need to remember, let's say, what is this function for, what is this for, and so on. Okay, so we go to the gated latch. Okay, let me see what is saying there. When the enable is low, the simplest SR has both input 0 and operates in the hold mode. Okay, in this mode, the old value Q is maintained regardless of the value of S or R. Okay, regardless of what your S or R, if your enable is low, okay, it will have both inputs 0 and operate in the hold mode. Okay, when the enable is high, just like previously, like multiplexer or whatever, when it's high, only then it start to operate. When the enable is high, the path for the SR signal is open. Okay, the path of the SR signal will be open. And the value of Q can be changed by entering the proper value of your S and R. The gated SR latch will enter forbidden state if we put both S and R high. Okay, so we have forbidden stage also. Therefore, we should not put S and R high when the clock is high. The alternative gated SR latch using NAND gate is shown in figure 110. Okay, this is the alternative using NAND gate. Okay, so now let's go to the, you see the function. Okay, so if the logic symbol, you should have SR and you have the enable. Okay, so this is as your output, which is, this is Q, of course, and this one is Q bar for sure, because it's inverted. So when you have an enable as 0, okay, when you have enable 0, regardless of what combination that you have for your S and reset, your Q, your next output will follow your current output, which is Q. Means this one simply means nothing's changed. Then the next, when you start enabling and you start the set and reset just 0, 0, this one seem inconsistent with the inconsistent with the SR latches, okay? Inconsistent with the SR latches of ungated latches. It's just that it have the enable. So when it have this 0 means just like the previous ungated latches, if it's 0 here, it will maintain the previous output, which is Q. This one is future output. So this is present, okay? Either you use present output. I think for me it's just the same, okay? If you have Q plus, this one you can have a present output, and this you want to call it future output. Or this is one, if you call this is post output, this one will be your outputs, okay? So it's just that this one must be after this one. That's all. The way you write or the way the question give you, you should be able to understand, okay? Then later on, when we start have 0 and 1, what happened? It will undergo reset, mean reset to 0. Then the next, when you have S1, then you will set back to 1. Okay, this is, and similarly as in a ungated latch, okay, if you having both S and R1, then your output will be forbidden. What happened here is that similarly, your output will be low. You cannot have both output Q and Q bar low, right? It should be reciprocate from one another. So that's why it's wrong. This one is called forbidden stage. So this is the timing diagram. You can just try to understand. Let's say if you have your enable here is 0, and this is S1 and this is 0, regardless of what combination you have here, this will follow the previous output, which is 0. This will be 0. When you start have enabling high, your S is 1 and this one is 0. This means it will set to 1, just like this. Here, set to 1. Then the next, when you have this still as 1 enable, and this one set is 0 and reset is 0, which is 0, that's why you have no change. So it will just follow the previous output, means nothing changed. And if you start to have enable low and S00, what happens is that it is also no change, means it just bring the previous level, okay? Then here, if you have this as 1 for enable and set is 0 and you have reset is 0, so what happened? It is no change, mean it just follow the previous output key, high, so it just follow high, okay? I think you guys this is quite understandable and straightforward, okay? So now we go to the next gated D-latch. A variation of the gated R latch is the gated D-latch, just like how is the variation of how is S bar R bar latches is a variation of SR latch. So similarly for gated D-latch is a variation of a gated SR latch, okay? They are performing quite similar, okay? Now a version of is the gated, okay, simply the D-latch. The D-latch is building by adding an inverter to the gated SR latch, okay? What is the difference is that when we go to our mind map, okay? We have gated SR latch and we have gated D-latch. What is the difference is that this gated latch is we have adding inverter. We adding inverter to the gated SR latch, okay? The difference, okay? Now the latch has two input, okay? Before that, let me see what is the circuit look like. 11.3b. 11.13b. 11.3b is here, okay? So you can see it's just adding an inverter, okay? They should put 11.13a, okay? Okay, they put it. So it's actually here. You added inverter at your SR latch, at your gated SR latch, then you have your gated D latch, okay? The difference between the gated D latch and gated SR latch, okay? Then this is simple modification to the current SR NAND latch, and this one is the when we have the rewired, okay? Means reconfigure. So sorry for the interruption, okay? And then so you have can see you can see the difference. Okay, you must able to detect the difference. Okay, you can see this is the same, and this one, it is carried here, we carry it to here. Okay, in order to have, like, the function is replacing the inverter. Okay, but you should able to differentiate the circuits. Okay, now the operations of this gated delay symbol. Okay, you can see if it's enable 0, okay, the D, regardless of what input of D, okay, you see the gated SR latch have two input, but for the gated D latch it only have one input, which is our D. Okay, which is our D. So if you enable is 0, means it will not do anything, then your Q future output will just follow your present output, which is Q. Then when you start enable 1, okay, when you put enable 1, this one will be 1, and this one is either 0 or 1, right? Am I correct? So here you are introduced with the concept of transparent. Okay, so I better read so that you guys understand. The D latch has two input and enable. The D latch is commonly used to store 1 bit of data, 1 bit, and to delay a signal by exactly 1 clock period. Okay, so it's either to store 1 bit of data, okay, this function gated D latch, or it can use to delay a signal, okay, by exactly 1 clock period. When the enable input is high, the output transparently follow the input. Okay, they are the same when we put this enable high. For this reason, the gated D latch is commonly referred to as the transparent D latch. So it have different name now. It can be transparent D latch. Okay. So when the enable is low, it holds the output to the logic value seen at the input, D input, when enable change from high to low. The logic symbol and characteristics about the low are shown in figure 11.14a, representing timing diagram for the D as shown in figure 11.15. Okay. So we continue. If you have enable which is 1, okay, which is 1, and you have your D is set to 0, what happened is that okay, I want to search the word from you so that you can see the proving. Okay, so if you enable is changed from high to low, so the output will be following the D. Okay, here the output will be following the D, which is 0. And what if your enable is high and D is set to high? Okay, when D is set to high and this one is set to high, so it will just, the output will follow the D, which is 1. So that's why we have two transparent modes here. Okay, where the output will follow the D in the condition that enable is activated, is enabled. Okay, so this is the timing diagram you can see and you can understand. Okay, you can try to see, you need to understand. Okay, don't just see it like this, you need to understand what happened, what actually happened between this, and then you're able to know the circuit really better. Okay, so you have, let's say you have enabled 1 here, then you have your D is 0. What happened is that it will just follow, the Q will just follow your D. Am I correct? The same with here. Okay, it just follow until here. When it's slow, what happened when it is slow? It just storing. Storing means it will follow the previous output, which is here, without considering the D, which is we ignoring. So that's why it's storage. Okay, it will follow the previous output here so just carry it here. Okay, and here when you set this as 1 and this is 0, okay, 1 0, it will be transparent, means your Q will be following your D, which is 0. Okay, I think this is quite understanding. Okay, so try your at your home, okay, to read and properly sit down and try to understand. Okay, for those who didn't have module, please finds your way alternative, maybe using getting soft copy or ebook, I'm not sure. You can try your way. Okay, I will not suggest illegal way, but you need to have some books to in order to read and to understand, right? So you guys need to understand really the operation in the timing diagram. Okay, so we finish with this what we call as the latches. Okay, now we go to the next concept. Okay, the next type, which is the flip-flop. I think flip-flop is famous before you guys even understand what is flip-flop definition. Normally we refer to somebody that always change principle, or always change their word, or maybe not consistent with their promise or word, whatever. We call this a flip-flop. So this is flip-flop. Flip-flop means always change. Okay, so let's we see for the flip-flop. Okay, we can see here, right here we have latches, flip-flop. Now we go to the last one, which is the flip-flop. Okay, not really the last, but yes, for this chapter is the last, but we have a lot of other flip-flop have a lot of family. Okay, I cannot draw here. So first flip-flop. Okay, so we can use here. Okay, flip-flop. So I will try to limit this video to only 1 hour. I know it's a bit boring and tiring to watch. Okay, but that's why I try to limit to 1 hour, and then if I don't finish it, we will continue. I will record another second video, 1 hour, something like that. And of course, I think you understand my condition, and I think you believe also that teaching is more exhausting. I'm using my voice and I'm writing and try to explain. It's more exhaustive, consume more energy than watch. Okay, and your part is the one that consuming energy is actually trying to understand. So we are both trying to sacrifice something so that all of the students pass. Okay, I don't want you guys to fail, of course. Okay, so please, even this video is long, you guys need to watch it. This is for you. If not it's okay, but make sure you don't fail. Okay, so now we go to the flip-flop. Okay, what is the difference between this flip-flop? In this section, we study another class of sequential circuit we call flip-flop. Flip-flop are circuits that are sensitive to these clock edges. Okay, clock edges mean right, low to high, high to low. Okay, clock edges like this, high to low or low to high. Okay, then this behavior is opposite to latches, which are sensitive to clock level. Latches is different because latches, they are more sensitive to clock level, which is 1 0 1 0, something like that. But the flip-flop is sensitive to the clock edges, which is high to low or low to high. Okay, they are different. So this is one of the main difference. So you need to know this in case it's asking in the quiz, the test. Okay, what is the difference actually between flip-flop and latch? Let's say they give you only 1 mark, so you only need to mention that. If they give 2 marks, you need to mention 2 difference. Okay, for example. Okay, so flip-flop activated by rising clock edge, which is a positive edge trigger, rising here, positive edge trigger, while those activated by falling clock edges are negative edge trigger, from here to here. So they have 2 operations. Okay, for flip-flop. So we have PET, positive edge trigger, and we have negative edge trigger. Okay, clock inputs on flip-flop are symbolized by triangle in logic symbol, the clock. Okay, the clock inputs, this you can see. So this is your clock. Okay, the bubble may be added to signify a flip-flop sensitivity to negative clock edges. Okay, if it's sensitive to positive edge trigger, we don't have to put anything. But if it's conversely sensitive to negative edge trigger like this, so you need to put a bar here. Okay, you can see the bar. So where's the eraser? So that you can see there is a bar. See, there's a bar, right? Now, so this clock flip-flop with different edge sensitivity. Okay. Okay, now we go to this master flip-flop. Okay, we go to master flip-flop. Master flip-flop, one way to make a storage element change outputs. Okay, so if we first go to this first type. Okay, master slave flip flops. Okay, one way to make a storage element change output only once per clock cycle, means when you have clock cycle it change only one, is by connecting to gated D latch. Okay, so it's using gated D latch, so it's using this one, gated D latch. Okay, this one, but it's using two in series. The configuration is called the master slave flip-flop because the second latch, this we call the slave, only respond to a change in the first latch. The master means there must be something change here, only then this one will respond. Okay, a master slave flip-flop based on the latches is shown in figure this 1.17. The master is enabled and changes its step when the clock is high. Okay, you see, clock is high, then this one is enabled. But you see, when this one is 1, this one will be 0. So when this one is able, this one is disabled. Okay, and vice versa. When the clock is high, the master track the value of input D. Okay, when this one is high, then the output, okay, will follow, will see the value of D. Okay, value of D, as it is a transparent latch. Okay, just like we gated D latch, we call it transparent. The output of the slave remains, okay, the output of the slave remains unchanged. Okay, however, when we start when the clock start goes low, okay, when the clock start goes low, means this is low, so this one will be disabled. However, this one low, high, then will be enable. So when this is enabled, this one is disabled. So the next, when the clock goes low, the slave will be turned on. This one will be like for example, like can imagine like turn off. Okay, can imagine. Okay, but it's not turned off. Okay, when the clock goes low, the master is disabled, but the slave, which is now enabled, copies the output of the master. So it will take whatever value of the master and will take as its input. The output of the master is locked as the latch is now disabled. Okay, lock. So whatever 0 or 1 value at that time, it will be locked because it is disabled. Now, therefore, we can say the master slave flip-flop can only change its output only during the 1 to 0 negative edge of the clock. Why? Because the output, the end output here, okay, only change when we have the negative edge of the clock. Okay, I try to find the word so that you can see. Okay, so it's the overall output will only change, okay, here when we have the negative clock. Okay, we have negative edge clock. Now let we see from this characteristic table, if your clock is 0, what happened is that you don't care what the value of D means. At Q plus, the next output will just follow the current output. Okay, and if you start have clock 1, what happened to your output? Also don't care of value of X, don't care value of D here. Okay, this means no change. It will still follow the previous output as it present output. Okay, previous output Q plus, we just take it. And when we start having, okay, if you see this is arrow, okay, arrow, and then when we start rising here, increase, and if your D is 0, your Q will just follow 0. Okay, this one is you call as a reset. Okay, the next, if you have that time, if you have that time D is 1, then you have Q is 1. Means it just follow the inputs. Okay, so D is your selected value. It can be 0 or it can be 1. Okay, so that's why this table you have 0 and 1. Okay, now a master slave flip-flop is pass triggered, as it requires both the rising and falling edges of the clock to operate. I think it's understandable, because for the master to enable it, it will require what? It require rising edge of the clock. Contradictory with the slave, to enable it will require falling edge of the clock. Okay, I think this understandable. At the same time, it is negative edge trigger, and is changed only as it change output only during high to low clock transition, because here, okay, this one is only changed if this is enable. This one is enable, which is negative. Okay, negative edge trigger. The master slave built with no base latch exhibit a phenomenon called 1S catching, a glitch in SOR while clock is high cause master latch to change. The NAND base latch has similar property called 0 sketching. During the first, okay, this 1 sketching and 0 sketching problems, to save our time here, okay, and I will share one video from the YouTube. Okay, there's a person explaining what is actually this one catching and 0 catching problem. Okay, so there is problem with 0 catching and 1 catching problem here. Okay, so due to the first catching problem, edge trigger flip-flop are preferred method to build synchronous logic circuits. Okay, due to this first catching problem, they are sensitive only during the rising or falling edge of the clock. Okay, this is for the first catching problem, because the window during which the inputs are sampled is small, any glitches that occur will be ignored. Okay, the window during the which inputs are sampled. So I will show you guys the other YouTube links. Okay, they will explain around, I think if I know second, around 5 minutes or 7 minutes about this. Okay, next we go to the next is which what we call as a D flip-flop. Okay, D flip-flop has 2 inputs. We have a clock input and a D, which for a data or delay input. Like the D latch, it is also used to store 1 bit of data or delay. Okay, so you need to understand. So D latch is either to store 1 bit of data or delay a signal. This one is also maintained. This users is also maintained by D flip-flop. Okay, however, unlike D latch, it does not have a transparent mode. Okay, so this is very important. Okay, you need to understand. The question can ask you, for example, in the final, in the test, for example, which one have transparent mode? Is it D flip-flop or D latch? You should know that, because this one may be 1 question marks. You don't need to do some proving, but you need to only answer true or false, something like that. Okay. Now, when a clock edge arrives, the input is transferred to the output. Okay, when clock edge arrives, the input is transferred to the output. The output remain the same until the next clock edge. Okay, the next clock edge come, then it will make changes outputs. Okay, the D flip can be either positive edge trigger, okay, positive edge trigger of the clock, okay, positive edge trigger, or negative edge trigger. Okay, for a positive edge trigger D flip-flop, the input is only valid or seen during the clock rising edge logics. Okay, for a positive edge trigger D flip-flop, the input is only valid or seen during the clock rising edge. Okay, so figure 8.1.8 show the logic symbol characteristic of table for D flip-flop. Okay, and figure 11.19 show the schematic diagram for a positive edge trigger D flip-flop. Okay, okay, so this is the D flip-flop. Okay, D flip-flop. think I'm sorry, there is a bit confusion just now, right? I'm using this to actually explain this master slave flip-flop, which is it's wrong. I'm sorry. Okay, so this one is for the D flip-flop. Okay, so figure 1.18 shows the logic symbol and characteristic table for D flip-flop. Figure 119 this displaying the schematic diagram for a positive edge trigger D flip-flop. Okay, this is you can see this schematic diagram for the positive edge trigger D flip-flop. Okay, figure 11.9 display a schematic. Okay, figure 11.20 compare D latch, positive edge trigger, D flip-flop, and negative edge trigger. So this one later on I try to touch it. Okay. Okay, so this one is actually this one is actually with respect to the D flip-flop. Okay, so wait for what, I think my battery is almost finished. I ran out of battery. Okay, I hope it's okay now. So okay, so where were we? Okay, so this is the circuits. Okay, now we go to the next, which is we call it as JK flip-flop. So JK flip-flop is the most versatile. Shows figure for 11.21 shows the logic symbol and characteristic table of the JK flip-flop 11.21. Okay, so this is your JK flip-flop, and this one is your JK flip-flop as well. You see, before the lecture teach the student, they are also reading and learning. Okay, when we try to teach you, we also need to learn. Means it's like double the effort. So teaching and learning is not the same. Teaching, in order for us to teach someone else, we must first reading, and we must first also understand before we can teach someone else. Okay, so means that I read this before I teach you guys, so you can see the pencil which I sketched. Okay, so the JK flip-flop is essentially a modified SR latch as shown in figure 11.22. Okay, here modified. We have seen that the SR latch operate in forbidden mode when both input SR are high at the same time. You see, right? When we have both high, then we have output low, which is forbidden, because we cannot have Q and Q bar having the same value 0 or having the same value. Now the JK flip-flop solved this problem by feeding the output back to the input. You can see it's feeding the output back to the input. You can see this is a JK flip-flop, and you can see the difference with the SR latch. Okay, where is your SR latch? Okay, here. Let me see. This is your SR latch. Okay, you can also this the same. This is using NOR, is using NAND. So you can see the difference is that feeding the output back to the inputs. Okay, but you see later on is with they will be from here going to there. Okay, instead of entering the forbidden state when both control inputs are high, the JK flip-flop toggles or inverts input. Means if we have you know, when in the SR latch, when we have S and R are both high, then they will be enter the forbidden state where we have Q is both 0 regardless of Q or Q bar. So this one, when we have both high, what the JK flip-flop do is that it will invert the output, the previous output. They say if previous is 1, it becomes 0 now. It just invert, toggle. Okay, so JK flip-flop, what is the difference? It have toggle function. Okay, JK flip-flop. The pulse detector shorten the clock pulse to ensure that the output toggles only once every clock edge. Okay, that's why we have pulse detector shorten the clock pulse. This one. So if question asks you what is the why we have pulse detector here. Okay, you should be able to see the answer. It is to shorten the clock pulse. Okay, it works because physical gate have small delay from an input change to output change. In Boolean algebra, a bar is 0. Theoretically, the output of the n should be high at all times. The delay in the inverter caused both input to the AND gate to be high for a short time, hence the short pulse of the input. Okay, you can see just like almost the same as like similar like I say when we have let's say why we add buffer. For example, why we add buffer? Because to the circuit, because we, even though the input and output from the buffer doesn't change, because we want to add delay. Okay, so this one is also the delay. Okay, so we want to use the function delay. Now trivia, the JK latch was named after Jack Kilby, the Texas Instrument engineer who invented the integrated circuits. Okay, Texas Instrument is one of the supplier which provide the measuring equipments. Okay, so it's we still have this company until now. Okay, so okay, let we see the latch. Okay, we see from this first. Okay, okay, this one is the latch. This one is positive edge triggered. I try to take the positive edge triggered flip-flop. This one is negative edge triggered flip-flop. Okay, positive edge trigger flip-flop, negative edge trigger flip-flop, and this one is your D latch. Okay, so this is what we'll touch this later on. Okay, so that you not confused. Okay, this we just proceed first with your JK flip-flop. Okay, so you see JK flip-flop, what is the famous function differentiated because it has toggle function with compared to the SR latch. Okay, so if you have a 0 here, it doesn't care what is your J and K. This is similar with your SR. So this Q plus will follow the output from previous, which is Q. Similarly, okay, then let's say if you have 1 here, which clock begin to set to 1, okay, regardless when you start, regardless of combination of J and K, okay, this flip-flop just like the rest, okay, they follow the previous output, okay, which is Q. Okay, when you set as 1, now let's say during the clock edge, okay, let's say we clock edge from low to high. Okay, from low to high, here is a positive edge triggered. Okay, then what happens is that for 0 0 it still follow the same output from the previous. Okay, your then when is the next edge trigger, they say we have JK here is 1, just like SR latch. Okay, this like function as reset, so you have resets. The next positive edge trigger, if your that time your J is 1 and your K is 0, then you have a set function. Okay, 1 0. Then at the next positive edge trigger, what if you have both 1 1? In SR latch, this is simply forbidden, but in JK we have this difference of operation, which is toggle. We will have toggle, so inverted of the previous inputs. Okay, so okay, we try to see. So this is the pulse detector timing diagram. Okay, you can see there's a small pulse. Okay, just like consistent as what the words say here. Okay, the pulse detector shorten the clock pulse to ensure that the output toggles only once every clock edge. It works because physical gate have a small delay from an input change to the output change. Okay, so the delay in the inverter cause both input to the end gate to be high for a short time. Hence the short pulse at the output. Okay, short pulse at the output. So you see, this is your clock. Okay, then you have your X and Y. Okay, I think they didn't label where is the X and Y. Past maybe is X and Y here. Okay, so let's say you have during the clock is this, you have, let's say this is 1, this is 0, because you can see it's always like opposite, okay, because you have not function. Then here when we have the clock which is rising, this is will be rise and this one will be 0, and you can see there's a small chance, a small delay. Okay, small delay. So when this is 1, this is 0, they will be slowly turning up. This will be slowly turning up. You can see slowly, it's not direct here, slowly. So this is the short pulse. Okay, next, okay, we try to see from this, we try to understand this fella. Okay, timing diagram for JK flip-flop. So you have this clock. Okay, when your clock is going high, from low to high, it's rising. So what happened is actually, okay, let me, so that I don't know how you guys can see. Okay, please compare this with this. Okay, try to see the relation. If the clock change from low to high and your J at the time is high and you have K is low, what is your Q? Okay, what is your Q? You see this one, and J is high and K is 0. What is your Q? Is this 1. Okay, then after that we have the same clock, and then at this time J is 0. Okay, J is 0 and this K is 1. Okay, J is 0, K is 1. But what happened is that it's only changed when we have the it's only changed when we have positive edge trigger. Okay, you can see from here. Okay, regardless of what is the value of your JK, okay, if it's not at the edge triggered, it will be having no change. It will follow the previous outputs. So that's why here, okay, here you can see JK, it will just follow regardless of what you have JK here. Your Q will just continue. Okay, it will, this Q plus will follow the Q here. Okay, the same when we have the next one, edge triggered positive, then J is 0 and this is 1. 0 at the positive edge trigger, you have 0 and you have 1. Okay, what happened? You will have reset. Okay, if you have negative edge trigger here, and that time your J is 0 and this is 1, so you have reset. You start to have reset. Okay, then similarly like this. Okay, then we see this one, edge positive edge trigger. This one similar as what I explained here. Okay, positive edge trigger, when we have increase here, means we start to see the J and K, right? So this is 0, this is 1. See, this is 0, this is 1. So it will have reset. Okay, then at the next positive trigger, edge trigger, we have both J and 1 is high. So you see positive edge trigger both 1. So you have toggle. it will be toggle, means from 0 to 1 or from 1 to 0. Okay, you can see toggle, right? Toggle is actually inverted from the previous outputs. Okay, so I know it's already 1 hour 10 minutes, okay, but I want to cover because I don't cover hanging, right? So you have D latch and flip-flop. Okay, so you can see this one is the D latch. Where is it? This one is D latch. This one is positive edge trigger flip-flop. This one is negative edge trigger flip-flop. So when you have your clock as set high, okay, means positive edge trigger, and that time your D is the time your D is 1. So what happened to the D latch is just, it will just follow. It's just follow your D for the D latch. Okay, this one is your D latch. This one is positive edge triggered flip-flop. This one is negative edge trigger flip-flop. Okay, this one is D latch. Okay, so how about this positive edge trigger? When this one is turned positive, this one will edge trigger will follow the previous the inputs, which is the D. And what happened to the negative edge trigger? It doesn't have any changes. Okay, because it's only respond to the negative edge trigger for it to have to consideration of the inputs. So during this positive edge trigger, your negative edge trigger doesn't have anything. Okay, but when we start falling, okay, when we start the negative edge trigger, what happened? What happened is that your D, you can see here, okay, in negative edge trigger we just follow. Okay, so when we see for the D latch, where is it? Oh, this one, D latch. Okay, where is the operation? Okay, I think this. Okay, so what? Okay, when this negative edge triggered, okay, negative edge trigger, you start to see the D. The D is 0, so it just this. Okay, and then for the positive edge trigger, okay, if it's negative edge trigger, it just follow the previous output to be the next output, which is this one. We just follow from this. Okay, until we face the next positive edge trigger, then we will start changes or considering based on the inputs of D. Okay, also same with negative edge trigger, it's only changed, for example, it's changed with respect to D when there is a negative edge triggered. Okay, otherwise it just follow from the previous output. Okay, as is next output. Okay, so what happened inside here? Okay, for example, this one is turned low. Okay, this one is still low, so you have your D, right? So regardless, because it's positive edge trigger, you can see it just follow from the previous input straight forwards. Okay, so how about this positive edge trigger? Because it's follow the previous input of high, so it just follow high. This one the same. Okay, D is low, so it just low here. Okay, so I think you guys can try at home. Okay, so with that we finish. Okay, we finish about I cover about latches and flip-flop, clocks, ungated latches, bistable, SR latch, SR latch, which is using NAND gate instead of the NOR gate, and I cover gate latches and gated SR latches, gated D latches, flip-flop, master flip-flop. This one, sorry, just now, this one is for the D flip-flop. Okay, not for master slave flip-flop. Okay, and then this one I cover the D flip-flop, which is, this is the corresponding characteristic table, and this is JK flip-flop, and then I also cover the JK flip-flop operations and the comparisons between the D latch positive edge trigger D flip-flop. D is input. I explain the comparison between the D latch, positive edge trigger D flip-flop, and negative edge trigger D flip-flop. Okay. So the next we will try to cover starts from the T flip-flop. Okay. So inshallah, see you guys in the next lecture. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good day everyone.